Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. And in this lecture, we're going to talk about how to prove that e to the x is actually equivalent to its Maclaurin series. So at this point, you probably should have just learned about power series and Maclaurin and Taylor series, and this little issue that not all functions are actually equivalent to their power series expansions or their Maclaurin or Taylor series, in that we also need to kind of prove that they are. And the way we do that is look at the remainder after you've taken the nth degree Taylor polynomial. Let me go ahead and remind you. And this is from the previous video, but the idea is that you have a remainder after you've added up the first n terms here. And so the remainder is just the difference between what the real function is and let's say, the summation of the first 10 terms of the Taylor polynomial. And you want that remainder to tend to 0. Okay, if the remainder does tend to 0, then you know your function is actually equivalent to its Taylor series expansion, or Maclaurin in the case of e to the x, because we're centering at 0. And the way you normally do that, because it's very difficult to actually do that mechanically, is that you use Taylor's inequality here. And Taylor's inequality just says, if we can find the n plus first derivative of our function, our given function, and we can find a bound for that on some interval centered around the center, A, then the absolute value of the remainder is going to be less than this expression here. Okay, so that's what we're going to deal with. We're going to actually take a look at the exponential function and try to bound its n plus first derivative on an interval about 0. Now, I should say, if that does not look familiar to you, you should watch the previous video in this sequence of videos. In fact, you should probably watch the previous few videos. So let's go ahead and do this. And I'm going to write down kind of our tactic, what we want to do. Now, we want to show that the n plus first derivative is less than some number, less than or equal to some number on a given interval centered around A. And I'm going to modify this in a moment to kind of be more conclusive about our situation here. And we want to do that so that the absolute value of the remainder, which is bounded by this expression, can then be limited down to 0. So the right-hand expression there, we want that to eventually limit down to 0. So that's our goal. So the first thing I'm going to do is I'm going to find a bound for the n plus first derivative. There we go. Scroll down a little bit. So f, the n plus first derivative of x, is forever equal to, in fact, maybe I should say in absolute value, is forever equal to just e to the x, because our function, remember, is e to the x. You take as many derivatives as you want, and that's still just e to the x. Now, on the interval, and we're centering because we're worried about the Maclaurin series, you're centering at 0. So on the interval negative d to positive d, and in fact, we are including the endpoints on this interval. So on the included interval, negative d to positive d, the absolute value of e to the x, well, the biggest it will get is, because we know e to the x is an increasing function, the biggest it will get is going to be e to the d. That's as large as it's going to get, and you can visualize that just with a quick graph if you want to. Here we go. We have some exponential function. Here's x equals 0. And then here's d right here, and here's negative d. And you can see the largest the function gets on that interval is this height here, which is e to the d. And in fact, if I really want to be exact about this, I should say it's at d comma e to the d. But anyway. All right, so I happen to now have a bound for the n plus first derivative on our interval from a minus d to a plus d, and like I said, those should be closed, but it's not that big of a deal for us right now. So I'll go ahead and cross that out. We're done with that. And now I want to talk about the remainder. What is the remainder? So I'll say hence. One thing I do want to say is that the remainder the absolute value of the remainder, is greater than or equal to 0, because I'm going to use that in this argument. But it's also less than or equal to, according to this statement here, that value of e to the d, let's go right here, divided by n plus 1 over times the absolute value of x minus 0 to the n plus 1. So I'll write that in. So it is, again, less than or equal to e to the d divided by the quantity n plus 1 factorial times the absolute value of x minus 0 to the n plus first power. Okay, great. We have that so far. Now, as you should be able to use all of your knowledge from previous math courses here, specifically your knowledge from Calc 1 using the squeeze theorem, I'm going to take the limit as n goes to infinity of all sides of this triple inequality. So just putting this in here. And one thing I am going to do is that e to the d power is a constant. It's not involving n, so I'm factoring that out. So I have the absolute value of x to the n plus first power over n plus 1 factorial. So we know that obviously the right or the leftmost limit is 0. And we still have this limit in the center. And now I'm going to pause here. I'll write e to the d though, times something. And we're going to talk about that limit as n goes to infinity of this absolute value business. So I'll put a little asterisk here so that I'm telling the world, guess what? You're going to look at my little note. And in fact, I might write that note a little bit further down the line just because it would be cleaner in the long run if I do that. So here's my note. We know that, well, actually, maybe I should prove it. So let me erase this and I'll just say, consider. We know from a previous video, but I'm just going to say, consider the summation n equals 0 to infinity of x to the n over n factorial. And what we're going to do is we're going to showcase that converges, or yeah, it converges. Yeah. So by the ratio test, and in fact, maybe I should even be better with this and say, just to convince people, I'll put an n plus 1 here and an n plus 1 downstairs to really make it convincing. Now, most people are probably wondering, what is he going to do here, or what is he talking about? You're about to see. By the ratio test, let's see, the limit as n goes to infinity of the absolute value of, remember, this is considered to be a sub n, so it's going to be a sub n plus 1 over a sub n. That's the ratio test. So the limit as n goes to infinity, absolute value of a sub n plus 1 is actually x to the n plus 2 over n plus 2 factorial times the reciprocal of a sub n, which is going to be, again, n plus 1 factorial over x to the n plus 1. And we can clean this up. You will have an absolute value of x that can be factored out. You'll have the limit as n goes to infinity. And again, this is going to be the absolute value of, you already took the x's out, and n plus 1, or I'm sorry, I should say n plus 2 factorial is the same thing as n plus 2 times n, oops, not an m, but an n plus 1 factorial. And so you see those cancel. So this is going to be 1 over n plus 2, which is going to be the absolute value of x times 0, which is always less than 1, no matter what. And that will imply by the ratio test that the series n equals 0 to infinity of x to the n plus 1 over n plus 1 factorial is not only convergent, but absolutely convergent. And that's important here. It's absolutely convergent. What does that mean, that it's absolutely convergent? It means that if I looked at the summation n equals 0 to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial, that would also converge. Now I'm going to hold you responsible for remembering another thing here. If you know a series converges, maybe I'll write this in a different notation or a different color here. So recall, if a series converges, that will imply that the limit as n goes to infinity of the sequence the series is based upon tends to 0. This is actually the contrapositive to the divergence test. Divergence test says if the limit for the sequence is non-zero, then the series that the sequence builds will not converge, it'll actually diverge. So this is the birthplace of that theorem. So this will imply, I'll get back to my black ink here, this implies that the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial will end up being 0. Now you might be wondering, what does that do for us? Maybe you're not, maybe you realize it already, but I'm going to highlight that because it's so important. And I'm going to scroll up here. Now remember, the limit as n goes to infinity of that absolute value of x to the n plus 1 over n plus 1 factorial, I know that will be 0. Let me scroll up and see if I can find that. Oh, look, right here. Isn't that the same expression? Sure is. And so I know that will be 0. Which implies that the right-hand side of this triple-sided inequality is going to be 0. Left-hand side is 0, so thus the limit as n approaches infinity of the absolute value of the remainder is equal to 0 by the squeeze theorem. I love it when we get to use a lot of the calculus that we've learned in the past. So what does this mean? It means that the remainder, so let me go ahead and cross this guy out. We've done that, and we've shown that the remainder tends to 0. So we've gotten everything checked off. That means that, well, actually, maybe I should show you that we are given a function e to the x, not assuming that e to the x is equal to that power series. We actually didn't bother computing the nth degree Taylor polynomial for e to the x, but what we did want to do is we want to somehow showcase that the remainder tend to 0. And that's exactly what we did. We found out that the remainder here tended to 0 by the squeeze theorem. So as long as the remainder tends to 0, oops, I should probably be right here. As long as the remainder tends to 0, I know my original function is actually equal to its Taylor polynomial expansion. Therefore, e to the x must be equal to its Taylor polynomial expansion about 0, or what most people would probably call the Maclaurin series, but whatever, x to the n over n factorial. QED. Proof is done. Now, I should mention that doing this is challenging, to say the least. In general, as you move forward through your Calculus 2 course, you might have one or two other times where you're going to have to prove that a function is equal to its Taylor polynomial expansion. But in the long run, we just say, well, let's go ahead and assume that it is equal, because the mechanics in the background end up becoming very tedious, somewhat reliant upon technology, and very challenging. Not that you shouldn't be able to do it, but you should be able to do it. But there are going to be a lot of examples likely in your course where your instructor just says, go ahead and assume that the function is actually equal to its Taylor polynomial expansion, and just find the Taylor polynomial expansion. Okay, that's it. I hope you enjoyed the video, and stay tuned for the next one.